Determine your location to the centimeter around the globe. For everybody, not only for the military. Only with an ESP32 and a decent GPS receiver module. Not possible. Wrong. It is possible. You can even earn some money by building your own base station and connecting it to a global network. When I got this board from Michael, a viewer of this channel, I was hooked on the idea of trying and understanding this relatively new technology. What about you? Interested too? Then follow along. Gritty YouTubers, here is the guy with the Swiss accent, with a new episode and fresh ideas around sensors and microcontrollers. Remember, if you subscribe, you will always sit in the first row. By the end of this video, you'll have a clear understanding of how it is possible to measure the distance to fast-moving satellites more than 20,000 kilometers away and use that information to calculate your exact position. You'll also see how this technology enhances standard GPS. To demonstrate, we'll use my do-it-yourself ESP32 base station. Connect it to a global network and see if it can really deliver centimeter precision. And finally, learn what DePINs are and how you can earn money with this technology. This isn't just about the technology, it is about the practical applications and the potential it holds for all of us. GPS was invented in the 1970s and implemented from the 80s on. In 1995, I had my first Garmin handheld GPS receiver for pilots. It was mind-boggling because from now on, I always knew where I was and where the forbidden zones started. A big stress reliever. The accuracy of this degraded non-military system was around 100 meters. Useful for pilots because they use wide airways, but not yet for car drivers. After the Gulf War, the US military stopped the artificial degradation of the GPS signals, and so improved its accuracy. I strongly suggest reading or listening to You Are Here, if you are interested in how it all began. Other nations like the Chinese, the Europeans and the Russians started to build their own GPS systems. Together they are called Global Navigation Satellite System, short GNSS. How does GNSS work? I will use GPS to explain it. The most important fact is, in 1 microsecond, light and also radio waves travel about 300 meters and 30 centimeters in 1 nanosecond. If we want to measure the distance with a precision of 3 meters, we have to be able to measure time with a precision of 10 nanoseconds. And if we want to measure 3 centimeters, we need to get to a precision of 100 picoseconds. Not bad. Keep in mind, these satellites are 20,000 kilometers away, move at high speed and have to have exactly the same synchronized time. At first glance, this seems to be impossible. But let's see how they manage to make it work. To determine its position, a GPS receiver needs to calculate the distance to at least 4 satellites by measuring the timing of the signals. For that, it listens to 1575.42 MHz, or L1, where all GPS satellites transmit their signals. In the meantime, other frequencies were added, mainly L2 at 1227.6 MHz and L5 at 1176.45 MHz. The engineers back in the 1970s had to solve 2 major problems. The first, how to decode weak signals traveling 20,000 kilometers through space. And the second, how to distinguish between signals of different satellites on the same frequency. Let's monitor these 3 frequencies with a Spectron SDR receiver. All contain more or less random noise with no visible carriers. Interesting. If I connect the same antenna to a proper GNSS receiver module, it shows my position. Obviously, there are hidden signals on these frequencies. How does this work? Back then, they decided that each satellite transmits its own pseudo-random pattern of 1023 bits with a rate of 1.023 megabits per second. This is the reason we can hardly distinguish them from noise. Because these patterns are known to all GPS receiver modules, they can compare the signals coming from all satellites with all known patterns. Mathematicians call this process cross-correlation. The result is a peak when the received signal pattern and the code of one particular satellite match in time. Nearly no peak is visible for signals of other satellites. So such a peak contains two parts of information. First, which satellite sent the signal, and second, its precise timing. The width of the peak is about 1 nanosecond or 30 meters. Even if you can determine the peak very accurately, the precision of this signal is limited to a few meters because there are other sources of inaccuracies, as we will later see. This is the precision of our smartphones, for example. After receiving the signals of all visible satellites, our GPS receiver knows the distance to these satellites. But only if the clocks of all satellites and our receiver are exactly synchronized. Keep in mind, a difference of 1 nanosecond means already an error of 30 meters. This is why all satellites have built-in atomic clocks that are regularly adjusted by ground stations. Our GPS receiver module has a clock too, but to save cost and space, not a very precise one. So the whole thing would not work unless we use a trick that is later revealed. The next problem: to get our precise position, we need not only the distance to the satellites. Our receiver also needs to know the momentary position of each satellite, also with a precision of meters. We will later see where it gets this information from. To calculate a three-dimensional position, the distance to at least 3 satellites and their precise positions are needed. The trick to work with the unprecise receiver clock is to use the signal of a 4th satellite to calculate the precise time. Now we are ready to receive the exact position with a precision of a few meters, everywhere on Earth. It's incredible, but it works with a receiver module for a few dollars and such tiny antennas. As said before, we want more. 100 times more precision. Sounds impossible again. Let's try to understand which problems we have to solve to get to such a precision. We have to be able to measure the travel time of the signal to the picosecond. We have to compensate for position errors of satellites to the centimeter. We have to account for time delays influenced by the ionosphere. The ionosphere is the upper part of the atmosphere and consists of charged particles. They are heavily influenced by the sunlight and therefore change all the time. And correct many more small errors in the overall system. Let's start with the first problem. Increase the precision of the timing. As we saw before, GPS has a modulation frequency of 1 megabit per second. But its carrier frequency is around 1.5 gigahertz and therefore a wavelength of around 20 centimeters. What if we would be able to determine where on this wave we are? Then we would know our position to the centimeter. Technically, the place on a wave is called phase, by the way. Problem solved? Unfortunately not. As shown before, GPS has a precision of some meters. Let's assume a precise GPS position of 5 meters. Then 20 wavelengths fit into these 5 meters. This is rightly called ambiguity because we know exactly where we are on the wave, but unfortunately not on which one. Not good. Clever engineers developed real-time kinematics, or RTK, to solve this problem. Let's assume you have two receivers close together. One is fixed and its position is exactly known. The other can be moved and its position is not known. Both measure the position with GPS and determine their phase. Because one knows exactly where it is, it can determine on which wave it sits and determine the actual difference between its position and the GPS position. If it would transfer this information to the second receiver, this one could determine its exact position too. And we solved problems number 2, 3 and 4. Because both receivers are very close, all these differences are nearly the same and are included in the correction signal transmitted. Cool. If we call the fixed receiver base and the second one rover, we have our RTK system. Of course, it is way more complex, but for today we stick with that. Fortunately, the distance between the base and the rover can be up to 20 kilometers. And the system still works. Next problem. How is this correction signal transmitted from the base to the rover? Here we have 4 typical scenarios. Directly by using a transmitter on the base and a receiver on the rover. High-end lawn mowers attach a base to the charging station and the rover to the mower. Also, high-end drones work with fixed bases close to the pilot. In this scenario, each rover needs a base station. Commercial base stations unfortunately cost a fortune. Via internet, the base and the rover are connected to a service. The base transmits the correction signal to the platform, and the rover receives a valid correction signal without owning a base. Signals can be transmitted via Wi-Fi or via mobile networks. There are many such professional services available, usually very local and very expensive because building and maintaining bases every 20 kilometers is not cheap. RTK2Go is a free service, but it only works if you have a base station in the vicinity. The closest one to my home is about 40 kilometers away. So later I will build my own for a fraction of the price of a commercial one. Via satellite. Companies like u-blox operate many base stations around the world. Because they cannot afford one every 20 kilometers, they place them about 150 kilometers apart and do some math to their signals. Like that, they typically get a precision of below 1 meter, but not to the centimeter. Still okay for many use cases and available globally, but not cheap. The board I got from incl offers transmission methods 2, 3 and 4. The ESP32 includes Wi-Fi and this 4G modem can connect to the next cellular tower. It even contains a satellite receiver that can receive u-blox data from space. They offer a limited service for developers free of charge, by the way. It also contains this small u-blox RTK receiver that covers the most important bands, L1 and L2, and shows its position on a map. So let's check how it works. As said before, I want the best precision, so I built a base station and connected to RTK2Go. We go away from the house to reduce signal reflections and start with GPS only. As expected, the position moves a few meters. With RTK enabled, this changes considerably. The position is solid. And if I move the receiver, or should I say the antenna, along a straight line, we see this straight line also on the map. Impressive! Also, small movements are shown quite well. Watch the scale, 20 centimeters. Here you see typical applications for RTK. Maybe something is for you. To build a rover, we just need an RTK-enabled GPS receiver and an ESP32 if we have Wi-Fi available. Plus Michael's Arduino software. SparkFun offers many such receiver modules and also wrote the required libraries. We know now that RTK works and we saw this rover board. But I also promised that you could earn money with RTK. How does that work? And how can we build a base station? Helium, with its network of LoRaWAN gateways, was one of the first companies that created a new industry called Decentralized Physical Infrastructure Networks, short DePIN. DePIN companies try to replace investors with crowdfunding. Like Helium, they create a cryptocurrency and pay the owners of the infrastructure with this currency instead of real money, till they get paid by the customers. Everybody who had to work with professional investors knows that this would be a very good idea for startups because often these investors are arrogant and a pain in the ass. People who watched my Helium video know that I was not happy about this company, mainly because there was no real business behind transferring LoRa messages. But is DePIN in general a bad idea? I do not know yet because it is too new. But I give it a chance if there is a real business case behind it. Selling RTK correction data seems to be a multi-million-dollar business already now. So this market should be better than LoRaWAN messages. And its future application is much broader. A few DePINs already tried to get such networks up and running. One of them is Onokoi. This network has two advantages. The first, they allow makers to create their own hardware and do not sell overpriced miners. And second, its president is one of the founders of uBlocks, a no-nonsense guy also with a Swiss accent. How can we build such a base station? You need 4 things to get the best signal and therefore the most rewards. A special antenna for all GPS bands, an RTK receiver for all bands, an ESP32, software to read the receiver and send the correction signal to the service. You can buy this receiver with an ESP32, but it is expensive and only delivers data to Onokoi. This is why I built one myself. Mine delivers data to Onokoi and RTK to go. I do not show how to build it here, but you can find links in the description if you are interested in this technology. Anyway, connecting 4 wires between the receiver and the ESP32 board and loading the software is all it needs. The rest is configuration. Keep in mind, commercial stations cost thousands of dollars. This miner still costs roughly $700, including shipping. My setup was less than $300. It's not cheap, but maybe I will get the money back or make more than I invested. It has already started to earn some cryptos. Even if I will not earn a lot, I had a good time learning and experimenting with this technology. It helped me to understand one of the key technologies of our civilization, and I pay respect to the engineers who, more than 40 years ago, believed that such a system was possible and started to work on it. Keep also in mind that GPS satellites synchronize most of our clocks and are part of each cellular tower, for example. I made a video on how you can use this precise timing for cheap in your lab. Jamming these signals seem to be a major threat during war times. I also promised to tell you how GPS receivers get the positions of all satellites. The pseudo-random code contains a very slow modulation that transfers all this data, also called almanac. It can take more than 10 minutes to get all this data. This is why all GPS modules have a small battery attached. They store the almanac data and because satellites do not frequently change their path, can use old data to get a faster fix. If the GNSS receiver has an internet connection like a smartphone, it uses assisted GPS to get this information much faster directly via the internet. This is why our smartphone nearly immediately knows its position. In this video, we learned that GPS needs extremely precise and synchronized time signals to measure the distance between satellites and our receiver. It needs at least 4 satellites, 3 to determine the 3-dimensional position and 1 to correct the time of the receiver. Its accuracy is limited by the slow modulation as well as by variable influences by the ionosphere, for example. If we want to get to centimeter precision, we need to measure the phase of the carrier signal as well as account for the real-time difference between a precise position and the signal. This difference is measured by a base station and transmitted to a roving station to enable the rover to solve the ambiguity and determine its exact position. The distance between a base and a rover should be below 20 kilometers to get an RTK fix. Commercial services sell such correction signals for quite high prices. RTK2Go offers a free-of-charge service but does not have broad coverage. This is why I built a base and connected it to Onokoi, a DePIN company that tries to build a global network of base stations and sell the data for a lower price. I will be paid in cryptocurrency for my services. Who knows if I will get the invested money back. This was all for today. As always, you find all the relevant links in the description. I hope this video was useful or at least interesting for you. If true, please consider supporting the channel to secure its future existence. Thank you. Bye.